Welcome, undergraduate and graduate engineering students. Today, we're diving into a full explainer on advanced control systems. This isn't just theory. We are establishing the precise academic foundation you need to master modern industrial controllers. All the material we'll be covering today was prepared by Dr. Nima Mahdian, and it's going to guide us through a really rigorous examination of these systems. So, let's just jump right in. Our overarching theme for this session is Advanced PID Control Architectures. Specifically, we'll be charting the evolution from standard parallel structures all the way to interacting series structures. Think of the concepts we're discussing today as the absolute bedrock. You really need this foundation to understand how theoretical control laws are actually adapted to survive the harsh realities of physical hardware out in the real world. Because let's face it, the core challenge we're dealing with is moving beyond textbook PID. Ideal equations are great, but they assume perfect sensors and perfectly smooth set points. Physical realities inevitably intrude. Just think about it. Sudden set point changes will trigger massive, damaging actuator spikes. This is what we call derivative kick, and it leads to huge, excessive actuator demand. On top of that, an unmodified derivative component literally amplifies high-frequency sensor noise, which can cause violent system instability. Modern architectures absolutely have to explicitly solve for these physical realities. So, how do we solve this? Well, our very first architectural solution is the IPD controller structure. To prevent that abrupt actuator damage we just talked about, the IPD structure strategically reorganizes the components. It places the integral element directly on the error path, E, while isolating the proportional and derivative elements over on the feedback path processing the output, Y. By doing this, we completely change how the system reacts. Now, any sudden set point changes at R are absorbed strictly by the integral action, totally avoiding those immediate nasty spikes on the actuator, U. And that brings us right to our second solution, filtering high-frequency noise. Because an unfiltered derivative action reacts so violently to sensor noise, we structurally require a low-pass filter using a divisor N. Mathematically speaking, the raw derivative block, S times T sub D, is replaced by S times T sub D divided by the quantity 1 plus S times T sub D over N. This structural transformation is a real game changer. It takes a highly erratic, unfiltered signal and mathematically forces it into a smooth, clean, filtered signal, ultimately safeguarding the actuator. Moving forward, we really must establish the time domain baseline. This foundational calculus expresses our controller output, U of t, acting upon the error, E of t, and the system output, Y of t. Now look closely here. In this specific IPD baseline, the proportional and derivative terms act on the output, not the error. Therefore, U of t equals our global gain k multiplied by the sum of our terms. That sum is negative Y of t for the proportional output plus 1 over t sub I times the integral of the error E of tau d tau minus t sub d times the derivative of the output Y of t with respect to t. So, you might be wondering, how do standard industry practices actually accommodate these necessities? Enter the ISA standard PID controller. Rather than shifting P and D entirely over to the feedback loop, the ISA standard introduces two critical degrees of freedom, weighting factors alpha sub P and gamma sub D. Here, the reference signal R actually splits. It passes through alpha sub P before being compared with Y for the proportional gain, and it passes through gamma sub D before comparing with Y for the filtered derivative block. These weights are brilliant because they allow engineers to surgically soften the impact of set point changes without having to sacrifice direct reference tracking. Let's systematically unpack the anatomy of this ISA control law in the Laplace domain. The total output, U sub ISA, equals the global gain K multiplied by three distinct terms. The first term is the quantity alpha sub P times R of S minus Y of S. Here, alpha sub P strictly scales the proportional response to set point changes. The second term is 1 over S times T sub I multiplied by E of S. This is the pure error E of S driving the integral. And the final term? It's S times T sub D divided by the quantity 1 plus S times T sub D over N, all multiplied by the quantity gamma sub D times R of S minus Y of S. This clearly shows gamma sub D scaling the derivative response to the reference, heavily filtered by that divisor N. Now, expanding out from the ISA standard, we encounter the general parallel architecture. This represents the ultimate structural flexibility. By placing independent weighting factors on the reference signal R before it even hits the proportional, integral, and derivative pathways, literally any parallel variant can be synthetically generated. We can track R splitting into alpha sub P, beta sub I, and gamma sub D. These weighted references are then compared against the feedback Y before entering their respective processing blocks, which ultimately yields the final filtered output. Manipulating those exact weighting vectors fundamentally shifts the controller's whole behavioral paradigm. Let's break down the configurations. For a standard PID architecture, alpha sub p, beta sub I, and gamma sub d are all configured to 1. For a PID architecture, alpha sub p and beta sub I are 1, but gamma sub d is set to 0. And for the IPD architecture we analyzed earlier, alpha sub p and gamma sub d are 0, while beta sub I is 1. Crucially, notice how the integral weight, beta sub I, remains strictly anchored at 1 across all of these configurations. That is a non-negotiable requirement to guarantee zero steady-state error. Contrasting with those parallel designs, we absolutely must examine the series or interacting PID structure. This architecture actually emerged from the physical limitations of early industrial pneumatic controllers. The series structure places the elements in a very rigid sequence. The arrow E enters stage 1, the PD stage, which generates an intermediate signal E1. This E1 then flows directly into stage 2, the PI stage. We call this interacting PID because tuning just one single parameter inherently alters the behavior of all downstream blocks. It's all connected. Looking inside the interacting series equation, the fundamental difference really lies in that intermediary signal, E1 of t. The series structure applies the derivative action first, creating a sort of new pseudo-error that is subsequently integrated. The parameters here, k superscript s, t sub I superscript s, and t sub d superscript s, differ entirely from their parallel counterparts. The output equation, u of t, equals k superscript s multiplied by the sum of E1 of t and 1 over t sub I superscript s times the integral of E1 of tau d tau. This crucial pseudo-error E1 of t is simply the original error E of t plus t sub d superscript s times the derivative of E of t. This brings us to a highly practical scenario. What if you're upgrading a legacy system? Well, if the series parameters are known, translating them into the equivalent parallel parameters is a straightforward algebraic process, and the good news is it's always mathematically possible. The parallel gain k equals k superscript s times the quantity t sub I superscript s plus t sub d superscript, all divided by t sub I superscript s. The parallel integral time t sub I is simply the sum of t sub I superscript s and t sub d superscript s. Finally, the parallel derivative time t sub d equals the product of t sub I superscript s and t sub d superscript s divided by their sum. However, converting a modern parallel controller backwards into a series structure introduces a strict mathematical limit. It is not always possible, folks. The translation math requires the parallel integral time t sub I to be strictly greater than 4 times the derivative time t sub d. If you violate this constraint, you end up with imaginary, physically impossible series parameters. The ratio of t sub I to t sub d must exist firmly in the feasible zone of real parameters, explicitly avoiding the constraint boundary where t sub I is not greater than 4 times t sub d. So let's synthesize our analysis by comparing these PID architectures directly. No single structure is universally perfect. The optimal choice depends heavily on the specific noise profile, legacy hardware, and setpoint tracking domains of your actual physical plant. IPD provides complete isolation to prevent derivative kick and handles high surge set points beautifully. The ISA standard prevents kick via weighting and serves as the modern industrial baseline. General parallel is fully configurable for custom structural synthesis, and finally, series does not inherently prevent kick. It features interacting parameters, and it's primarily utilized when interfacing with legacy pneumatic systems. To wrap things up, we conclude our executive summary with 3 defining system limits to take away from this explainer. First, real-world interventions. Standard textbook structures demand structural pathway alterations to survive high-frequency industrial noise. Second, surgical weighting. The ISA and general parallel architectures utilize weighting factors to establish 2 degrees of freedom, perfectly balancing disturbance rejection against setpoint tracking. And finally, the translation barrier. Backwards translation to legacy series structures is definitively governed by a rigid physical mathematical barrier. You now possess the solid academic foundation of advanced PID control. But the real question remains, when you step onto the floor of a multi-million-dollar industrial plant, which architecture will you trust to keep your system from tearing itself apart?